Okay, we've talked about a lot of variables, but you may wonder, how do we actually use gases in chemical equations? How do we use the ideal gas law to apply to an actual chemical reaction? And we can do this, and the crucial point here is the variable N. N is the number of moles, and remember that chemical equations relate everything in terms of number of moles. So if we're doing a reaction that involves gases, we can relate the pressure, volume, or temperature of the gas to the chemical equation through the number of moles of that gas. So let's go through a couple examples. First, the metabolic oxidation of glucose in our bodies produces CO2, which is expelled from our lungs as a gas, as shown in this equation here. Now, calculate the volume of CO2 produced at body temperature, which is 37 degrees Celsius, and slightly less than standard atmospheric pressure, 0.97 atmospheres, when we've got 24.5 grams of glucose that we consume. So how do we even approach this? Well, we approach it by solving for N. What we need to do is we need to find the number of moles of CO2 using standard stoichiometric calculations, right? We're given a mass of glucose, and then the other things, the other values that we're given are variables that relate to the ideal gas law. So temperature, pressure, those were given. We're asked about volume. We can't directly get volume from the chemical equation, but what the chemical equation does allow us to calculate is the number of moles of CO2. So if we do normal calculations to find the number of moles of CO2, then that will get us N, which we can then substitute into the ideal gas law. So let's go through that process. The first thing that we do is we start with the mass of glucose that we're given, and then we need to convert that to moles, because the chemical equation only relates things in terms of moles. So first, we will kind of take this approach to it. We'll start with our mass of glucose, we'll convert that to moles, then use the coefficients of the balanced chemical equation to convert from moles of one substance, glucose, to moles of another substance, CO2. And then once we've got moles of CO2, then we can figure out the volume of CO2. So we take our 24.5 grams of glucose, we calculate the molar mass of glucose, and convert this to moles, normal stoichiometric calculations. Then we use the balanced coefficients of the balanced chemical equation, so 6 moles of CO2 for every 1 mole of glucose, and we come out with a certain number of moles of CO2. We don't have to worry about significant figures at this point. We will correct for that at the end. And now that I know N, I can rearrange the ideal gas law to solve for V. So V is equal to nRT over P. We substitute moles in, we substitute the gas constant in, we change 37 degrees Celsius to Kelvin, and we divide by the pressure, and what we come out with is a volume of 21.4 liters. So consuming or going through the metabolic oxidation of 24.5 grams of glucose, you would then exhale in a continual process, not all at once, but you would exhale 21.4 liters of CO2 from that process. Let's go through another example. Let's just calculate the volume of oxygen that you would need at 1 atmosphere and 298 Kelvin to completely oxidize 50.0 grams of glucose. So our process, again, is very similar. Grams of glucose to moles of glucose. Moles of glucose to moles of O2. Moles of O2 to volume of O2. So anytime you're given a problem like this, where you're asked for volume, or you're asked for pressure, or you're asked for temperature of a gas, but you're not given the number of moles of that gas, and you have some balanced chemical equation, you're given a mass of something entirely else. Start with the mass, convert it to moles so you can use the chemical equation. Use the chemical equation to convert from moles of substance A to moles of substance B, and now you'll have the moles that you need to use the ideal gas law to figure out the missing variable, whether it's pressure, or temperature or volume. So here we will start with grams of glucose, convert that to moles of glucose, and convert that to moles of oxygen as we did before. 1.665 moles of oxygen we come out from this. And then now that we have moles of oxygen, we rearrange the ideal gas law. V is equal to nRT over P. We substitute these values in, the number of moles, the gas constant, the temperature, the pressure, and we come out with 40.7 liters. So you would need 40.7 liters of oxygen to consume just 50 grams of glucose. 50 grams is a decent amount, but still you could probably fit it in maybe on a small plate very easily. So you can see why we need to continually breathe in and out constantly in order to live, as we need to intake oxygen to be able to do this, these metabolic oxidation. So this is how you use the ideal gas law in a chemical equation.